Thank you. Thank you very much for both the introduction and especially for inviting me to come here. I feel like I should start with a warning. I'm not going to be presenting any new exciting results today or any new exciting methods. Nothing new and exciting at all, really. But I thought it would be nice to just take a little time to consider how amazing some of these models and methods that we're using really are. Because, I mean, they really can seem like magic, thereby the title. And it's easy to become a bit blasé and start taking some of this stuff for granted. And I think along with that comes the danger of taking for granted that the models are actually doing what we think they're doing or what we want them to be doing, which of course isn't necessarily the case. So, oh, no effect. Yes. Who am I to be talking about these things? I would definitely not consider myself an expert on the topic, but I have worked with a variety of sort of mark recapture style methods, including integrated population models, multi-state models, multi-event models. I've worked with a variety of systems. I use both the Bayesian and the frequentist framework. I have to admit I'm a Bayesian at heart, but I have quite a bit of experience with both. My background, I'm an ecologist by training, but I've been combining it with math from the very beginning. So I understand some of the technical stuff, but certainly not all of it. And I'm basically going to be using some examples from my sort of early days in mark recapture to think about these topics. But I would say that this presentation is just as much inspired by my conversations with students that I supervise and teach, and the way that they think about and talk about mark recapture models. So my introduction to mark recapture modeling came when I was asked to join the Svalbard reindeer project. So Svalbard is an archipelago that's halfway between the Norwegian mainland and the North Pole. And on this group of islands, there's a separate species of, subspecies of reindeer, which logically enough is called Svalbard reindeer. They've been studied quite extensively, and we have mark recapture data going back to the sort of early to mid 90s. In addition, we have structured count data annually from this population, and then there's harvest and carcass data. And so I was asked to build an integrated population model to bring all these data sources together with the goals of, first of all, learning more about the dynamics and the demography of the system, and having a model that could then be built on and used to look at other questions in the future. So, for example, environmental effects. But maybe just as importantly, to get a good estimate of the population size and to confirm that the counts were actually good counts. So if you're going to start with mark recapture modeling, why start simple if you could jump in at the deep end? So here is what in the paper is described as a simplified overview of the most important parts of this model that I built. It became quite complex. I'm not going to be going through this. I would need my whole talk just for that. But as an introduction, I mean, there was definitely a really steep learning curve here, but I think it was also really good because it forced me to think about absolutely everything I was doing, and how it was influencing the model, how it was influencing the results. Everything that I did here had to be really carefully thought through. And I think that's a good introduction to how one should work with this type of model. But so when I had built this model, started running it, getting out some results, that's when I got my first sort of taste of what I'm now calling the magic of mark recapture. Because I realized that we could actually get out estimates of calf survival from before they were marked. So the calves in this system are born in sort of early June, but they're not marked until April of the following year. But because we have this census data from August, where we then get some information about the calves, we were able to estimate calf survival from August to April, which I thought was really cool. And in addition, because of the mark recapture data, we could estimate the age structure at a finer scale than what was in the census data. So to me, this seemed like magic. But here's the thing, it was understandable magic. At this point, I could still see where this information was coming from, right? I could see how the model could do this and why it was possible to get out these estimates. But still pretty exciting. So then I presented these results to what I like to call the reindeer people. They thought they were neat. That was fun. Then they asked to see my estimates of population size. And they said, no way. This is wrong. Your model doesn't work. You've done something terribly wrong. And that's because this population was considered to be really easy to count. The landscape, the behavior of the animals, it was believed that the counts were close to the truth. And here I came and said, well, actually, there are about twice as many animals as you're seeing. They said no. The magic faded. But then I realized, but hang on, if these animals are really that easy to count and to see, there shouldn't be a lot of zeros interspersed among the ones in your recite data, right? So that's a relatively easy thing to go in and look at. And in fact, yeah, there are a lot of zeros there. So with time, I managed to convince both myself and the reindeer people that actually these are realistic population estimates. But what was really neat was that in addition to the census data that I had put into the model, we actually had independent count data from the same population, the same area, the same years. Why did this happen? Well, because there were two groups of researchers that didn't want to collaborate. Which seems a little bit silly given limited resources and all, but for me it was great, right? Because I had this completely independent data that I could then compare to my estimates. And this independent count was, the census was much more consistent from year to year than the one that I had used in my model. So this census was really focused on staying consistent, so they walked the same transects over the same period of time, same observers every year. And what was really neat here was that my estimates actually were more closely correlated with this independent census data that had not gone into my model at all than with the census data that I had used to build the model. So then the magic was back in full force. And at this point, I realized that, okay, this is not going to be the last time I work with this type of model, because this is really cool. Now, of course, in most cases, you're not going to have independent counts of exactly the same system. In fact, we don't have that anymore either, because in 2008, the two groups became friends and realized they could collaborate. So now we no longer have these two independent data sources. But I still think, so now we're getting a lot more data than we used to have. And the thing is, when I was telling people about this work, probably the most common question I got was, but why didn't you put all the data into the model? Why didn't you use this? Wouldn't it have improved your model to use this data as well? And in fact, now after the fact, when we've been using this model for other things, we have also built in that data. But I think it's almost like, as ecologists, we're so used to having not enough data that we have this need to put everything we can into the model and use, squeeze everything we can out of the data. And now we're starting to see, we're getting more data, we're getting new types of data. And sometimes it might be worth just sort of pausing for a moment and thinking, do we need to put everything in the model? Or are there times when actually some of this data could be kept out of the model and used to validate and test instead? So it's just a thought. After this, at this point I was thoroughly sold, but still skeptical because I'm skeptical by nature. And the next project that really got me skeptical was this one, which you already heard about yesterday. It's very nice because you got a nice intro to the SHAG project from Paul's and Rita's presentations. So I don't have to go through the whole system for you. But basically, what I was interested in here, so you already heard about these storms. This is the shags on the Isle of May. A lot of data available here too, long-term data. And there was this year, 2012-13, when we had these terrible winter storms. A lot of birds showed up dead, as you've already heard about. It affected their survival. But I wanted to know whether it also caused a non-breeding event. So non-breeding events where you get a lot of adult skippers are known from this system previously, but just based on nest counts. And we were interested in, first of all, whether this storm actually had caused a non-breeding event, and also whether we could find out more about the demography of that event, what types of birds were skipping, what was really going on. The problem was that we have no confirmed non-breeders in the data. So if individuals are seen breeding, if they're seen doing some activity that has to do with breeding, right? If they're building a nest, if they're on a nest, if they have chicks, like the picture in the middle here, you can say these are definitely breeders. If you see an individual that's hanging out on a rock, okay, you're not seeing it breeding, but it could still have a nest somewhere, right? It could be a breeder and you just happened to see it when it was hanging out on a rock. But it could also be a non-breeder. And so there's really no way in this system to confirm that any of the individuals are non-breeders. Multi-event models were suggested. You can have uncertain breeding states. And I thought it's worth giving it a go, but I really didn't think it was going to work, because how in the world could a model know if you don't have any confirmed non-breeders, you just have breeders or unknown breeding state? How could that possibly work? Now this has been done. There are examples in the literature where it has been used on systems like this, but at the time, this is quite a while ago. This is one of these guilty conscience projects that still hadn't been published and should have been published years ago. At the time, it hadn't been done, and I asked several people, some of which are in this room, whether they thought this was possible, and everyone said, we don't know. So I figured, okay, I'll give it a go, but really just to prove that it doesn't work, because then I can move on. So I built the multi-event model. Again, not the simplest one, because there were also some other issues in this population. And among other things, there are different parts of the island that have had different levels of field work. So different effort going into identifying parents at the nests, for example, which then has to be accounted for. But so I built my model, put in all the things I thought needed to be included, tried to run it, and it gave me some estimates. And I was amazed. It actually gave me some estimates. And not only did it give me estimates, but it gave me estimates that seemed to make sense. So this winter storm in 2012, these are the transitions from breeder to non-breeder. So in other words, probability of skipping as an adult breeder. And you see that it's very low, and then in that year with the bad storms, it goes up. That almost seems like something worked here. And in fact, the earlier years here, which you see I faded out, and I'm going to talk a bit more about why, but that 2004 number is also a known breeding event, non-breeding event from previously, from just based on nest counts. So this seemed like maybe something had worked. But then I started thinking, well, we know that the survival changed in that year. There are probably other things in the system changing. How do we know that this is actually a good estimate, a true estimate, not just that the model had so little information in order to come up with this estimate that it kind of used the other information it had, and there are actually other things that are driving this. So I decided to run a simulation study to try to see if I could parse out what was really going on here, and if there was reason to believe that these models could really do this. And for that, I had a feeling that the one parameter that would be really important was, oh yes, magic again, was this probability of identifying a breeder as a breeder. So if an individual is in fact breeding, what is the probability that we will see it doing something which leads us to identify it as a breeder rather than just noting it down as unknown breeding state? And again, because of the complexities of the system, this had to be estimated separately, both for we had some higher effort areas, so more field work, and some lower effort. We also had changes from year to year, particularly in periods. So in later periods, the fieldwork effort was higher. In some of the earlier periods, it was really, really low. And so these are the estimates that the model was giving. And we can see that in the high effort areas, in the high effort years, it was being estimated as really high, right? This probability of identifying a breeder as a breeder. But in quite a few of the years, it was sort of 30, 40%. And then we had some years where it was really, really low. So the first thing I wanted to find out was whether the model was actually estimating these things, these probabilities, properly. So basically what I did was I simulated data. And this is probably going to be a bit hard to see, but that's okay because you don't need to get involved in all the details. But I simulated data that sort of reflected the real system in all the important things. And I let the breeding probability vary stochastically from year to year. And then I put in 2 non-breeding events. And those non-breeding events, I either let the probability of skipping go very high or just sort of increase a little bit. Or I also had some examples up here where it didn't change at all. In addition, so the numbers that you see at the top are these probability of identifying a breeder as a breeder. And here I'm showing you one 75% and one 25. So a bit lower than the best we had, a bit higher than the worst that we had. In addition to this, I included all of the things, all of the assumptions that I thought could potentially be violated in the system. So this is not everything. There were a whole bunch of simulations I ran. For example, we didn't have enough data to estimate the detection of pre-breeders and adult non-breeders separately. So those that hadn't started breeding yet and those that were skipping. We had reason to believe, it seemed logical, that the detection of them should be about the same, but we didn't know. So I also ran simulations where I let the detection of those two be different in the simulations, but then ran a model where we assumed they were the same, right? Did everything I could to try to test any assumptions that I thought could be violated. And what I'm showing you here is, again, this probability of skipping or of moving from breeder to non-breeder. The dots are from the simulations. That's the true answer. And the blue lines are what the model is estimating. And we see that when this probability of identifying a breeder as a breeder is quite high, these models are actually doing incredibly well. There is some uncertainty in the estimates, sure, but it's picking out these non-breeding events and it's estimating things quite well. I have also looked at all the other parameters, but this is the one that I was really interested in. We see that when this probability of identifying breeders as breeders is lower, the model struggles a bit more. The uncertainties become more erratic. And there are some places where it doesn't do that well with the estimations, but pretty much it still manages to pick out the non-breeding events, and certainly does better than I expected. Maybe the most interesting case is this one here, where I actually didn't put in a non-breeding event, but I did change the survival in those years. And we see that when the probability of identifying a breeder as a breeder was low, it did start to sort of kick out estimates saying that the skipping probability was going up in years when it wasn't. At the same time, though, this was not in the years when the survival was changed. It was just random other years. And you can see from the uncertainty that there is something going on here. So probably if my output from my real data looked like this, I would have realized something was up. So this is one of the reasons why I faded out the early years. In the early years, we had low effort in the field work. We know that the data from those years isn't that good. And so I'm less confident in those estimates, in sort of the numbers that are actually coming out. But overall, and also, I mean, it was the later years that we were interested in, right? It was that 2012 event we were interested in. But overall, I have to say, I was amazed at how well these models were performing. even when I was violating assumptions left and right, it was still managing to pick out the important things in the simulated data. So definitely magic. And the point I want to make here, which actually is really nice because others have made it before, and Mathieu made this point even better yesterday, that I think this type of simulation is an underutilized tool. We tend to use simulations a lot when we're developing new methods and we want to show how they're working. We're not as good at using them to sort of test our empirical studies and see what would happen if our assumptions were violated, right? We're very good at writing our paragraph in the discussion about these are the assumptions and this might not be true. But there are quite a few papers I've read where I've thought, you know, I would find it a lot easier to trust these results if you could show me a simulation study. So yeah, just my thought of what maybe we should be doing more of. Now, a lot of what I've been talking about has been about assumptions. The explicit ones we make in our modeling that we're very aware of. There are ones that are more hidden that we're maybe not as aware of always as we should be. But there's one type of assumption, and this is slightly different topic, but there's a type of assumption I've been thinking a lot about recently and talking to a lot of people about, and that's the assumptions that we make in the data cleaning process. Because I mentioned I've been involved in work with a lot of different systems, and whenever I'm going to analyze someone's data, I always try to get to be able to participate a little bit in field work and a little bit in data cleaning just to sort of understand where the data is coming from. And what I've noticed is that every single system has these assumptions that are made very early in the process, long before we start analyzing the data. Often they're based on some observations that were made, 30 years ago or whatever, when the project was started. And they can be things like, well, this species, they never breed before age X. So if we see breeding activity before that age, it's kicked out. That can be done at the observation stage, that you just don't note it down because clearly it was wrong. Often it's done in the data cleaning stage. It can be automated scripts that we have made that we just run every year that goes through and removes the things we know aren't possible. The zombie individuals, the ones that were already dead and then they appear again, all these things. But quite often there are also these assumptions that, it's quite possible that that was true 30 years ago, and it might be true still today. But if we stick with this example of age at first breeding, we know that that can change. We know that, for example, climate can cause it to change. Changes in density. There are a lot of populations that are a lot smaller now than they were 30 years ago. So maybe it has changed, but if it has changed, we'll never know if we're kicking out that data before we ever look at it and start analyzing it. So just something to think about. And the reason I'm mentioning this is because, like I mentioned, I've talked to a lot of people about it, and I tend to get two responses. Either people get defensive or they say, oh, you're right, we should go back and think about this and maybe reconsider some of those assumptions. And so I think there are a lot of systems that could benefit from just going back and re-examining the assumptions and making sure that they are still good assumptions and still valid. Okay, so what do I want you to take away from this talk? Stay vigilant and always question everything, even when people get annoyed, because I do and they do. But I mean, this point would be easier to make, right, if I could have shown you that one of my models failed hideously. I still have that to look forward to. So I didn't have an example of that, but I think it's a very important point. And coming back to this, talking to students, it's so important that we're kind of aware of this and that we're constantly thinking about it, because we have things like goodness of fit models, and it's so easy to just run it through the standard tests and say, oh no, it's fine, right? But especially a lot of the models that we're using today are quite complex, and it's not necessarily that easy to find standard tests that will tell us what we need to know. So just to always think about what more can we do to make sure that the model is doing what we think it's doing. And maybe most importantly, remember to appreciate the magic. And again, this goes back to, what better place to appreciate the magic than this week, right? We have a whole week of magical presentations here, but also bringing this back to our students, right? making sure that they understand both of these points, that yes, these models are amazing. Don't just take them for granted, but also be aware that you still need to make sure they're really doing what you think they're doing. So with that, I would like to thank the organizers for organizing this amazing conference and also for inviting me. All my collaborators, field workers, funders, there were too many to list that have been involved in these projects that I mentioned. And also everyone who's willing to discuss research with me and listen to me ramble on, which now includes all of you guys. So thank you.
Okay. Time for questions. Thank you very much.
Thanks. That was a really nice overview and some really thoughtful questions that we need to think about. I'm just wondering, do you think these approaches can also be useful for trying to target more the things that we need to try and collect better data on?
Absolutely. Especially this idea with using simulations, something that I think is extremely useful for pinpointing both where we're missing information, but also what data we could be collecting that would be the most informative for the questions we actually want to answer. Yeah, it's a very good point.
Well, I have a question. You mentioned about checking the assumptions and be wary of the violation of assumptions. I was wondering if the simulations obviously helpful, but if they are enough for checking the assumptions, or should we really be looking into what's happening in the field, or you know, to the other side of the story, we will be developing goodness of fit testing and model validation, and not be just looking at the, you know, the biases and precision in the simulations.
Yeah, absolutely. I totally agree with you. I think this is only one piece of the picture. And also simulations, they can be really good. They can also be a little bit dangerous because of course we're making assumptions in our simulations as well. And hopefully we would be very, at least thoughtful and be aware of the assumptions that we are making in our simulations. But of course, you know, if there are things that we've never thought about in the data and those are causing the problem, we're not going to think about them in our assumptions either, or sorry, in our simulations either. So, I mean, definitely simulations are not going to solve everything by a long shot.
Thanks for that. And I agree that a lot of these models seem like magic to me still. I gathered from one of your closing points that you'd be an advocate for sharing data and sharing code, but maybe beyond that, sharing dirty data and data cleaning code as well?
Yeah, I think so. And if nothing else, being better at being sort of aware of what we're actually doing and being open about that. And things like, you know, when doing field work, often there are there's a set protocol and there are things that are decided, and then the field workers, be they students or whoever, they come and they're trained and they're told that this is the way it is. And eventually the original people tend to disappear out of the system, and all of the people who are left have often been trained in this is the way it is. And I think that just being more aware of that can be helpful. But also, to me, I think it's really important to make sure that we actually keep all of that data, because I have been involved in systems where, you know, one thing is what gets put down in the field notebooks, but then you had someone sitting and entering the data and kind of removing the stuff from the field notebooks that they didn't think could be correct. And that means that the data that gets put into the database, which is what the only thing that anyone typically looks at afterwards, has already been cleaned, but that's often not written down anywhere or noted anywhere. It's just that one person who thought to himself, this can't be right, I'm not going to put it in, right? And just sort of being aware of that and maybe being more open about that is, I think, an important thing. And then being able to go back and check, right? Has this changed?
Thank you for the very interesting talk. So in my experience, one of the issues that often comes up is when there is a mismatch between the population or the system we're trying to make inference about and the data we're actually collecting is not matching that. And so I was wondering, and I think that's very common, on program like field protocols that are just collecting data on the field, not thinking about how to analyze it. But still people have in mind, I want to make inference about this, but they don't realize the mismatch. So I was wondering if you have any word of advice on how to deal with that and how to make sure this mismatch doesn't happen.
I mean, I think it's a hard question, right? Because especially in a forum like this, where we're dealing with a lot of long-term data, it's really hard to look into the future and predict what type of data could be useful for questions that they're going to want to answer 10 years from now. But I mean, I'm very much on the side of note down whatever we can. As much as possible, think thoroughly through the questions before deciding setting up the protocol. But again, that's hard to do, especially in long-term systems. But I also think we could be better at planning for the best utilization of data. And this comes back to sort of a slightly different topic. I've been working on multi-species models and sort of moving more into the multi-species world and community world. And I think it has often struck me that if we, instead of all studying our own little population in our local place, if we had planned a little bit better so that we were studying some of these species in places where they actually live together. Often they are found together in the places we're studying them, but we're studying species A over here and species B over here. And if we had thought ahead and planned a little bit better, we could have been studying them in the same place, and then we would have had a lot more data for actually moving into the more multi-species models. And again, that's not a criticism of the way things are. It's extremely natural that it is, but I think as we're moving into a world with more data, bigger data, more open data, these are things that are worth thinking about, whether we can also come together and sort of plan things a little bit better so that we're not just collecting the data that's good for our study, but that can also be used for answering other questions.
Okay, with that, thank you very much. And that concludes this session. So I have you join for the next one.
Very short break. Only 15 minutes late.
Sorry, I'll put it back.
Maybe I have to put
Xin cậu. Yeah. Yeah. Okay.
Talking all the time. Just need to stand somewhere where I can actually see this.
So your last name is. Oh, so you told me. Okay. So I know. Okay. And then
No, if she's French from before, but I don't know if she's French.
Okay. Okay.
Oh, I have his name in
Okay. Okay. Actually, okay, yeah. Give it a talk. Yeah. What's that? Is it mostly online? I think we're mostly live. Yeah, I'm not entirely sure. Yes, well, I guess we'll see. There's at least 3 of you.
I'm super excited about it.
You're super excited about it?
Yeah.
Okay, good.
Excited for the problems, like, I feel like the whole community sitting on the fence, waiting for this to actually be solved usable, how you average this. Everything is waiting, right? So we're all sitting.
All right. Okay, sounds good. All right. Okay, sorry. Let's see. Okay, thank you. Yeah. Oh, yeah, All right. Okay, I think we're going to get going here. We're going to try to run kind of a tight ship here, given the excursions are coming up. So let's go ahead and get going with the modeling vital rates and space and time section. And our first talk today is Chloe Nader. She's going to be talking about an integrated distance sampling model to estimate variation in demographic rates across space and time. And she's very excited to give this talk today.
All right, so this was already teased a little bit on Monday when Alan was presenting the distance sampling monitoring scheme for grouse in Norway. So as a quick reminder, we have transects all over the country where people and dogs go out and count grouse species, and first and foremost, this willow ptarmigan. So these are trained citizen scientists, and that means they're able to not just kind of count the number of ptarmigans, but they can also, as they collect their data, make distinctions between males and females and between juveniles and adults. And that's additional information that we can take advantage of when we model these data and want to learn about population dynamics. So if we think about this ptarmigan population that consists of juveniles and adults, We have adults producing juveniles according to some recruitment rate. And we have both juveniles and adults that can survive to the next year. Now, the distance sampling data gives us information on both the number of juveniles and the number of adults in the population. And via age ratio, it also informs this recruitment rate. In the primary study area, there was also some radiotelemetry done. It's a small study, few individuals, few years, but sometimes these small studies make all the difference in integrated setups. So that's what we have for this integrated distance sampling model. And like a few details that may be of interest to some of you are we're modeling continuous observation distances using HARF normal detection function. And it's implemented in Nimble, which also allows us to use custom distribution and functions to make everything run a bit more smoothly. So what we get out of this model is for every location, we get predictions of population size or population density over time. In this particular location, we had an average population growth rate of about 13% over time, but you can see this fluctuated quite a lot. And especially in recent years, there have been some increases. And looking at the survival and recruitment components, we see it's mostly due to survival, and that aligns with the changes that were made to harvest regulations in recent years, which probably led to a decrease in harvest mortality. So recruitment rates also vary a lot over time, but they tend to be somewhere between 2 to 5 juveniles per adult. And if we average survival, we're somewhere around 34%, but again, quite a lot of variation between years. But let's remember that we don't just have single locations. And as Alina was just mentioning in her talk, we have to stop doing just single locations. So the monitoring scheme contains about 2,000 transects that fall into 41 management reporting areas. And that's really the scale where inference can inform management and be useful in practice. So for scaling up a model like that, what it means specifically is there's going to be an additional area index throughout the model. Note it's not on the telemetry because that we only have for the one area. And we can use hyperparameter distributions, which means that, for example, for average survival, we can say that the average survival in each location comes from a joint distribution. And then we get maps. Everybody loves maps these days. So this is a map of predicted population growth rate for the 3 most recent years across the different reporting areas. And we see it's a mosaic of lower and higher values, but most of them are positive. What people like to forget when they do maps is that that doesn't mean we got rid of uncertainty. So on the right-hand side, you can see a map of the standard deviation, there we go, of the posterior distribution. That shows us a little bit where we need to be more careful in interpreting results. So the dark values are places with higher uncertainty in estimates. We can make the same kind of map for the decomposition into survival and recruitment rates. And what we see here is, again, many colors, but quite strikingly, the brightest colors, or the highest survival rates, are all the way in the north. And those are also the areas where recruitment is lowest. And that's kind of consistent with previous studies and observations that ptarmigans actually have slower life histories further north. So further north, we have higher survival and lower recruitment rates. And then we get these really nice hyperparameter distributions that tell us something a bit more about species in general than about species in specific locations. So before I wrap up, I just want to say that we are building this model for management, And this means it's something they're going to want to rerun when new data is collected, when additional information becomes available. And rerunning large models can be quite a challenge, especially if you didn't very carefully document your workflow. So that's why we're working with this R package called Targets. And it's essentially a workflow setup, management, and running tool. It makes this really nice graphical representation where you can see which parts of your workflow require updating. And also if something goes wrong, it tells you exactly where it went wrong and due to which function. So it's much easier to debug it if you encounter problems while rerunning. I can recommend it. I'm never going back. And in the spirit of reproducibility, you can find the whole workflow and all the code on GitHub. Note it's not the main branch that has the multi-area implementation. There's some challenges remaining, like quite a few of the time average vital rate parameters are what I call unhappy chains. So something's not quite right here. These random effects models aren't working. And if we look at the temporal distribution, we see why, because that's not normal. And for this particular system, we think it may have something to do with these guys. So rodent abundance is actually quite an important indirect driver of population dynamics for grouse. So as a next step, we hope to include rodent abundance, which is also collected as part of the distance sampling survey as a covariate, and see if that helps making some of those change happier. The other thing that might help is like acknowledging that things in space aren't independent, and start thinking about to what degree we can use spatiotemporal correlations to make more efficient use of data. That being said, I haven't done that yet. So if anybody has thoughts or experiences with this, like, please come and talk to me. It's going to happen soon. And preprints will also be coming soon. So stay tuned. And I have some amazing collaborators. And I also want to thank all the people involved in data collection and curation, funding, and a special shout out to Michael Scroggy, who made this nimble distance package that made my life a lot easier. And then I'm happy to take questions.
Okay, thanks, Chloe. That was a great talk. We do have time for maybe one or two questions.
Yeah, hi, thank you for the talk. I'm just curious, I might have missed it. When you're doing like distance sampling for, this was willow ptarmigan, right?
Yes.
Is it like based off of like hearing a cue from them and trying to estimate the distance, or is it like visual sightings of it and estimating the distance from there, or?
It is visual sightings, but the sampling is done with teams of 2 people and 1 pointing dog. So it's the dogs finding the bird, and then they get flushed, and that's when the people count them.
Hi, thanks for the talk. Here, I'm used to thinking about slower pace of life in the tropics when we think about gradients for passerines, latitudinal gradients for passerines. So I was surprised to see the slower pace of life in the northern latitude rather than the southern latitude. Is there a biological explanation for this already, or some hypotheses that you can relate?
I think there is a lot about this. This is like, as we also heard at this conference, sometimes it's the oldies or goldies. I think there's a lot of work from like the 60s, 70s, 80s, 90s, when traditional life history theory was a thing. But I don't recall all the details, but we know, for example, that animals also tend to have larger bodies in colder regions because of the kind of the surface to volume ratio for heat conservation. And typically we get slower life histories in larger bodied animals. So I'm not quite sure what's the chicken and the egg here, but it is a known pattern, I think.
Okay, let's cut it off there. Thanks again, Chloe. And our next talk is Franzi Korner, giving a talk on demographic indices from constant ringing effort sites in Switzerland.
Good morning, everybody. I'm happy to introduce the current state of constant ringing effort in Switzerland. Oh, that was wrong. Constant ringing effort sites have been established in the 80s. Today, we have around 500 constant ringing effort sites in Europe and over 1,300 in the US, where they are called MAPs for monitoring avian productivity and survivorship. In Switzerland, we started 2016 with 15 sites, so CES is something brand new for Switzerland. The usefulness of CES has been shown many, many times. The most important aims is the early detection of threats, particularly in long-lived or mobile species. Changes in survival and reproduction can manifest years before we see a change in the population size. CES are also used for the identification of causes of population changes, and they provide estimates of demographic parameters that are important for management and research. So CES is an integral part of a demographic monitoring. They provide data for estimating survival, reproduction, proportion of transients, dispersal, and from Paul's talk yesterday, we now can add phenology, which I think is great. CES are done on many common bird species, but also not so common bird species. In Switzerland, at our Swiss CES stations, we have 4 or 7 capture days during the breeding season with a constant number and position of nets. The nets are controlled every half hour, and the birds are ringed directly at the nets and released directly at the nets, and every bird is noted independent of how often it has already been caught during the same day. So to analyze the data, we aim at using a standard routine, such as the R-package Cesar written by Rob Robinson. But currently, in the current state, we use JAGs to have more flexibility to explore the possibilities. So the general idea is to use a mark recapture model to estimate annual apparent survival, capture probability, and the proportion of transients, and then derive the population of breeding adults that are the non-transient adults as a function of the number of captured adults, capture probability, and the proportion of transients, and estimate the population of juveniles as a function of the number of captured juveniles and capture probability, and then use the ratio between the number of juveniles and number of adults as a reproduction index. So the data we collect in Switzerland have a double robust design. That means we have a primary period, which is the year, and a secondary period, which is the day. And when we assume no mortality during the breeding season, we have a robust design to estimate apparent annual survival probability. And then we have a tertiary period, which is the half-hour net round. And when we assume no mortality or emigration during the 7 hours of capturing, we have a second robust design to estimate the proportion of transients that we do only for the individuals captured for the first time. So this model is nothing new, it's just put together from earlier work. We estimate the proportion of transients for every capture day independently. Capture probability, we estimate for every site and year and different between the ages. And annual apparent survival, we estimate for every year and different between the ages. So from this, we can kind of directly extract an index or report the apparent survival over the years. I think that's all fine. The next step is still work in progress, the reproduction index. We were a bit on a time constraint because we had to report to the Swiss authorities how useful our test data is, and therefore we chose something quick that works. So now I'm here to collect better ideas of you. What we did is, so for every captured day, we have the number of captured, or the number of recaptured individuals and the number of firstly captured individuals. And from the mark recapture model, we have an estimate of the proportion of transients among the firstly captured individuals. Then what we did is that we summed up the number of recaptures with the proportion of non-transients, the estimated proportion of non-transients among the number of firstly captured, rounded to the next integer. And then we used these 4 or 7 counts as repeated counts of the number of breeding adults and used an admixture model to estimate the number of breeding adults. So I asked for an example data set, a small example data set of the reed warblers for 4 sites and 5 years. The estimates for annual apparent survival look very reasonable. We have a higher survival for adults than for juveniles, and we think it might be worth considering an interaction between age and year that would allow to report a separate survival index for adults and for juveniles. The proportion of transients is shown here for 4 sites. The panels and 5 years are the colors, and the x-axis is the date. So what we see is the proportion of transients is high at the beginning of the season. It drops during high breeding season and maybe may increase later. So this reflects the occurrence of migrants of this species. However, the uncertainty of this estimate is kind of large. So we think it might be valuable to think about species-specific constraints that are like informed by the phenology of the species. When calculating this reproduction index, we realized that when we correct the number of captured juveniles for the capture probability, this inflates the uncertainty of the estimates of the reproduction index, because the capture probability of the juveniles is estimated to be very, very low, particularly in some years at some sites, and then we get very unrealistic reproduction indices. So we decided to just use the raw number of captured juveniles and divide that by the estimated number of adults. And then we think we get kind of nice reproduction indices. So we think it looks promising that we will be able to report some useful reproduction indices after having done some more work to the model, revising this estimation of the number of adults. And finally, we would like to implement the model into CESAR. Thank you for your attention.
Okay, we have time for a couple questions.
Maybe I can answer Stephen Bailey's question already. No, we haven't accounted for changes in capture probability over the season yet, but it's on the to-do list. I think it's important.
It wasn't quite what I was going to ask. But thanks. It's really nice to see the way it's developed. CS is developing in Switzerland. I saw in some of your analyses you were looking at the same-day recaptures. Experience about what assumptions one could make about same-day recaptures, because I might expect, for example, a bird that's been caught once might remember and avoid that net, or equally, some birds having been caught might move a few hundred meters away and reduce their probability of being recaptured. So I just wondered whether you've been able to look at that at all in terms of checking assumptions that would be required to use that.
Yes, I think we see that in the juveniles. So we have about 10 times higher recapture probabilities for the adults than for the juveniles. And I think juveniles, once they have been caught, they might just move away or just sit somewhere and not move at all. Whereas the adults who have to feed juveniles, or have a nest, they stay active. But this is something we have to look more deeply into.
Thanks.
Hi, thanks for a nice talk. I was wondering, since you probably catch quite a lot of different species, and we know from like occupancy modeling that we can really learn more about rarer species by having these multi-species model. Are there any thoughts or plans for like integrating the analysis of the different species?
Yes, this is still a thought. But this is, yes, I think it's something we need to do, or would be valuable to do. Thanks.
Yeah, thank you for the talk. For the transients, yeah, for the transients, of course, we think about the late migrants. But my feeling from the analysis of sales data, it's also that we have transients all throughout the season because of breeding failures. And then with the juveniles, it's really not just the juveniles that were born locally, but they move around. So then the concept of transient and closeness of the population may be, yeah, the origin of the transients may be to be thought about.
So for the juveniles, we haven't estimated transients. Juveniles were assigned to non-transients. So the proportion of transients is only estimated for adults now. And yes, they were also transients during the breeding seasons.
Okay, thank you. Thank you, President. Okay, our next talk is by Cyril Milleray. I hope I said that correctly. Okay. He's going to be talking about mapping population-level mortality risks of an emblematic and controversial large carnivore, the wolf.
Good morning, everyone. So I will talk about our work on mapping population-level mortality risk of wolves in Scandinavia. So we know that individuals are not exposed to the same conditions. Depending on the location in space, they might be exposed to different pressures, they have different opportunities, different access to resources. And at the end, all of this is shaping the population, what we see and what we perceive from the population. So here is density map of, estimated density map of wolves in Scandinavia. So that's what we see from the population, but to understand what drives and how did we get here? We need to look a little bit behind, and we need to try to know where individuals are dying and where individuals are surviving. But to do so, we need long-term individual information about individual information in space and time, basically. So we use the amazing monitoring program of large carnivores and wolves in Scandinavia, which basically consists in non-invasive genetic sampling. We use 7 winters of monitoring data, and all this data is actually shared between Norway and Sweden, so 2 countries, and they share the data in a online database, Rovbase. And the effort is quite amazing and quite huge. So over the 7 winters, field workers, they performed and recorded more than 1.5 million kilometers of search effort. And that led to the genotyping of more than 15,000 samples that belong to more than 1,300 individuals. And we also had access to legal dead recoveries, because all dead shot individuals are genotyped as well. So even if this data is amazing, it's still not perfect. We don't detect all individuals, and we certainly don't detect all mortality events. So what we did is that we use an open population spatial capture-recapture model, OPSCR, to account for imperfect detection. So this kind of model, they have an observation process, And we accounted for spatial, temporal, and individual heterogeneity in detection. I will not go into details in this talk, but we have a set of covariates to account for spatial and individual and temporal heterogeneity in detection. This kind of model has also a population dynamic component where we model the recruitment and the survival and the death of the individuals. And it has a model that tries to look at where individuals are located in the landscape and also the movement of individuals across years. So if we do this correctly, which means we model movement correctly, we should be able to actually estimate true survival. But the key thing of this model is that since it's a spatially explicit and individual-based model, we can link the survival and the death of the individual with the location of the individual. That means that we can extract, based on the location of the individual estimated by the model, we can extract any spatial covariates and use those spatial covariates as an individual covariate on survival and the death of the individual. What is also very interesting with this model is that this model are built to estimate density. So we actually have a map of density. We know we have an estimated map of local variation in density, which we can also use as a covariate on individual survival and the death of the individual. All of this into the same model. Yeah, that was two wolves. So we built this Bayesian op SCR model using the R package Nimble and Nimble SCR. So to go to the results, what we obtain is a map of density for a given year here, and a predicted map of survival, which was based on a set of many spatial covariates and including local density, which varied every year. And what we did is that we combined both maps, first to be able to make predictions where wolves are actually located, but also to somehow represent the uncertainty in where wolves are located. So you see this blurry area where we basically have a little bit, yes, thanks for the light, we have a bit more uncertainty on the location of the wolves. And what you can see is that it's quite some spatial variation in predicted survival here. And basically what we see is that all these yes, northern area here, the western part of Norway, the northern part of Norway, and the northern part of Sweden is basically an exclusion zone for wolves. So a wolf that enter this zone is almost systematically shot. So the model is able to capture this spatial variation and predict basically a null survival of wolves in this area. But because we also had access to all legal mortality events, we were able to distinguish between mortality causes and also try to explain spatial variation in cause-specific mortality. So legal mortality, we had a perfect detection. All of the legal mortality events were recorded and all wolves shot were genotyped. But then we had all these other wolves that died, for which we basically don't really detect them. It includes wolves that died due to natural causes of mortality, due to poaching, due to traffic-related accidents. And for most of these mortality events, we don't detect them. And so using this kind of model, we were able to look at the spatial determinants of cause-specific mortality. I will not go into too much details because that's the work in progress right now, but just on the density dependence. So as I told you, we were able to look at the effect of local density experienced by a wolf on its survival and or its death in this case here. So if we look at the effect of local density on the effect of legal mortality, we predicted a positive effect of local density on the legal mortality rate, but a negative effect on these other causes of mortality. We still are trying to explain all these results because there are still correlations, so we need to understand what's going on. But the interesting part is that if we would have probably looked at it only on the survival, overall survival, we would have probably not been able to detect such an effect of local density. So to summarize here, I think non-invasive genetic sampling, and if you have also information about legal mortality, together with OpenSCR model, Open Population Spatial Recapture model, is a promising tool to really look at patterns that we probably wouldn't be able to show otherwise. Of course, it is not perfect, but when we see such spatial variation in this map, it seems that we somehow need to take into account the spatial variation if we want to make inferences about ecological inferences, but also make predictions for the future of this population or give recommendations for the management of these species. And plus, this non-invasive genetic sampling, especially in this case, really allows you to get a comprehensive sampling of the population. And this SCR model, which allows you also to account for imperfect detections, should allow you to get this population level mapping. So it's probably a very promising tool. Of course, we fitted this model to a huge data set. I know that it's quite amazing, but we have demonstrated in this paper that we can fit such models to smaller data set, about 70 individuals detected over 4 or 5 years. So it's possible to fit such models. But at this scale, that was only made possible by the use of Nimble and also the use of our packaged Nimble SCR model, Nimble SCR. Yeah, that was it for me. So thank you.
Thanks, Cyril. Time for a couple questions.
Does the other mortality overlap with reindeer management districts or areas where there's free-range sheep that would give a hint for causes of possible losses?
Yeah, the other mortality, you mean? Yeah, actually, if you, I don't know. Well, on the map, no worries. You remember all this red area, the northern part? Yeah, it's actually the sheep grazing area and the reindeer area. Yes, this all this area here, and it's actually basically very little wolves that died due to other causes of mortality. They mostly died due to legal mortality, or at least that's what the model predicts. And we have very few occasions of wolves wandering in this area. That answers your question.
Okay, then there's another question there, and then I have one online.
Sorry? Do you need the map? Yeah, maybe. Yeah, if I understood correctly, you predicted the highest survival very far south of the country. Is that correct? Not from this map. It was another map.
It was. It's probably, I don't know. I cannot really move. I think. Okay.
Yeah. Yes. So the blue we see on the left.
Yeah.
Do you know why the wolves are not there yet?
Yeah, so I think there are several reasons. It's also a high agricultural area here, so it enters conflict with people, and it seems that they have a hard time to actually go south, and they are colonizing and expanding into the south of Scandinavia, but very slowly. There's also another, I don't know if it's a problem, but this area is not very well covered with snow. So the sampling, which is mostly based on snow, is harder. But yeah, it's they're coming south, and it becomes a problem definitely in this area.
Okay, and then online, Chris Sutherland asks, what is the underlying density model here, and what is the driver of spatial variation in density?
Yeah, so that's a very good call. So we try to explain spatial variation in density using a set of spatial covariates. So the issue is that wolves are quite plastic, and so it's actually difficult to predict where they would be based on the landscape. So we used something that is a little bit circular, which is probably a weak point in our model, which is the location of packs. So every year this monitoring records the location of packs, and we believe that density is driven where packs are located. And where packs are located is not really explained by any spatial covariates. So that's the way we explain this. Just to answer Chris, also we tried a model without this density covariate, and actually we got exactly the same results. And we believe it's because the sampling is so high, such a high density sampling that yeah, this covariate doesn't matter so much because we already so much sampled.
Okay, great. Let's thank Cyril again. All right, and our next talk is Brady Matson. He's going to be talking about importance of biases associated with ground counts of nestlings.
Thanks, Paul. I just wanted to start off by acknowledging my co-author, Rahel, sitting there towards the back. She's sort of the big brain behind this project, and I still owe her a couple beers for all the work she put into this. I don't need to tell you that integrated population models are useful for integrating data for different demographic parameters, but what we do a little less of is integrating data for a single demographic parameter when we have multiple methods. And I think that's going to be increasingly important as we scale these models up to broader scales. I also wanted to point out that we also know that integrated population models are useful for characterizing uncertainty for the individual demographic parameters, including reproduction. And this is the focus of my talk today on this part of the population demographic process. And I think we could all agree that we can get accurate counts of young at nests. If it's an open nester like a piping plover, we can even count these young from afar with a spotting scope without disturbing the parents that much. And then we can also say we're fairly confident in the predictions from the integrated population model in terms of the extinction probability under various scenarios for management. But if we look at other species, like tree nesters, we may not be as confident about the number of young in that nest. So I don't know if any of you can get an accurate count of the young in that nest, but I think I would struggle with that. But we could get an accurate count by putting a mirror pole up to the nest or climbing the nest, but of course that causes disturbance. So we face this trade-off, I think, between accuracy and bias. And with this bias, we may not be as confident about our predictions using a population model under various scenarios for management. So we may not make as good conservation decisions if we just ignore this bias. And so our research question is basically, how important is this uncertainty about reproduction for making population projections? And this is relevant for several species, not just birds, but also potentially for mammals. And so to tackle this question, we use a simulation study that was based on empirical data that we collected on red kites. I'll just show you in a moment where we collected the data from, but just a quick summary. This project was part of a broader effort to attach satellite transmitters to red kites in several countries in Europe. And so we sent observers to go out and count the young from the ground right before the climbers went up to attach the transmitters, so that we had this combination of ground counts and climb counts for each nest. And these ground counts varied from 5 minutes all the way up to over 2 hours, quite variable depending on the logistics that the climbing crew had to deal with. And then we simulated the ground counts and the climb counts as truth. And so here's the distribution of nests that we monitored for the 2 years, for a total of 26 nests, mostly in Germany and Austria, but also a few in Slovakia and Hungary. We used a multi-state model that took 2 states, a number of nestlings from 1 to 4, and we had uncertainty in terms of false positives and false negatives when the ground counts were trying to get an estimate of number of young in the nests. And then we modeled true number of nestlings as a categorical, and then allowed us to get an expected number of nestlings in the nest. So let's just assume that there's 2 nestlings in the nest, but from the ground, you may only count one of the 2. That's sort of the setup that we were facing. And so the model assumes, well, that all allowed us then to model the ground counts also as a categorical, where we had this P parameter as the cell probabilities, basically under a given assumption for the number of young from the climb count, then we get an observed count, and that allowed us to estimate these cell probabilities. And I'll just refer to these as P. So we know that these counts can be biased high or low, but we only allowed it to be plus or minus 1 from truth in the model, which helped to fit the model. And that was also based on empirical data. And then we also made this optimistic assumption that the probability of getting an accurate count is higher than the probability of getting an inaccurate count for each of those counts. We used a log linear multinomial that allowed us to have these probabilities close to the boundaries of 0 or 1. And we had some issues with convergence, so we ended up using some moderately informative priors that had these non-divergent log probabilities. So we had to do this trade-off between convergence and bias, but we didn't have to struggle that much. So it was actually quite good with the convergence. And we implemented the model in R and Nimble. We had 3 questions we wanted to address with this study. The first one was pretty basic, just how many paired counts are needed to get a good estimate of P. Second, would it be better to have additional ground counts or to stick with a relatively small sample size of the climb counts? Because we know there's a potential bias with the ground count, so maybe it's not worth adding those to the sample. The third question, the most interesting one we really wanted to get at was, if we get an estimate of fecundity just based on ground counts, what if that's different than in the fecundity of the nests that we count with a more intensive method where we do the climb counts? And so this is where we really wanted to test the performance of the estimation model. We looked at a range of sample sizes from 10 to 250 and simulated 100 data sets for each of those, taking the random draws of the counts. And we looked at 3 levels of fecundity based on a literature review. And those p-values were based on our own data that we collected, that we used to set up the simulation. And then allowed us to estimate the level of bias and the coefficient of variation for fecundity. So let's move into the results. We found that based on the simulation study, it would be required to have at least 50 nests to get a good estimate of these p-values. So along the x-axis are all those individual cell probabilities based on the true counts and the observed counts, all the possible combinations of those. And then the y-axis is just a level of bias for those p parameters. So you can see that the bias was quite low, especially once we got to 50 nests. Second question was to look at whether it's worth collecting additional data from ground counts in addition to that small sample of climb counts. And the answer was yes, we did reduce the bias, but the bias was actually quite low, even with a small sample size of climb counts. But that was still interesting. We found that just using the raw ground counts gives us an underestimation of, and would be biased low if we just were to use the ground counts. All right, then moving on now to the most interesting question about whether we can get a good estimate from the ground counts, even if there's a heterogeneity in the fecundity between methods. And the answer was yes, we did get a good estimation that there was low bias when we were correcting for the bias in using estimation model. And so that was a nice result, that the estimation model was performing well, even under heterogeneity situation. And then moving into even the most interesting question, I think, of this effort is to see, what does this mean then? Okay, we found some bias from just using ground counts, but what does that mean in terms of population projections? And so we developed a population model and ran some simulations to test the performance of our estimation model. We found that the estimation model was very close to truth. It's the more narrow dashed line that is really close to the solid line, which is the simulated truth. Whereas the raw ground counts, if we just use those are biased quite low, and especially we had a large amount of bias in the larger population. So this was a scenario with a growing population, but we also looked at this in a declining population, and we found the same pattern where the estimation model did a good job of predicting the population trajectory, whereas based on the raw ground counts, that was biased low. Okay, so to summarize, this estimation model did a good job correcting for this bias associated with ground counts. And we found, based on the literature, the sample sizes are quite low when they're taking estimates of fecundity at a subnational scale. Of course, if you do a national level study, you have a bigger sample size, but if you're really interested in management relevant questions, you want to have a good estimate, I think, of fecundity at a finer scale. So these finer scale studies have a fairly low sample size. compared to what we would recommend is at least 50 to get a good estimate of not only the P parameter, but also fecundity. And we found that this bias associated with the ground counts could lead to inaccurate population projections, especially in larger populations. And that if we use the estimation model, then we can correct for that bias and get a better estimate of the population. All right, so what are we going to do next with this? This is a good start, I think. We've got an estimation model that does a good job, but now we want to think about covariates because we can maybe even get a better estimate of this, or better correct for the bias if we include covariates related to observation time, distance, and also the true number of nestlings as a latent parameter, which might require some reparameterization, but I think would be a nice way to try to incorporate that. And then we want to also look at covariates for fecundity itself, so we can ask questions relevant for conservation or for ecology. And then what we'd like to do is actually build this up into a network integrated population model. And I'm actually looking for a postdoc at the moment, I have a proposal that's in review, but I haven't identified someone yet to take that on. So if someone's interested, please send me an email or contact me after the talk. And finally, I just want to thank everyone that contributed. It was a great team effort. And I'll just leave it there and thank you for your attention.
All right, thanks, Brady. We have time for one question.
Thank you for your talk. So I was wondering, sorry if I missed this, did you consider that the probability of overestimating with the ground count was the same as underestimating? And do you think that this could be implemented in your simulation? Just because I was thinking that it's probably more likely that we see one less nestling than there is, than that we overestimate the number of nestlings.
Yeah, I mean, we use the empirical data to set up the simulation, where we did tend to have more underestimation compared to overestimation. So are you suggesting the other way around, or? No. That's, yeah, but that's basically what we had in the simulation study, yeah.
Okay, thanks again, Brady.
Okay.
Okay, the final talk in this session is by Joanna Farr. I don't know if I pronounced that correctly, but looking forward to the talk.
Thank you. So this work is part of my PhD research, and I work with Mathieu Auty and Florian Pollard on this study. So just to give you a little of context of my PhD, I work on the vulnerability of skate captured as bycatch, so as non-intentional catch in the toothfish fishery in Crozet and Kerguelen in the Southern Ocean. And skates, as elasmobranchs in general, and as birds and mammals, display particular life history trait that makes them particularly susceptible to population declines due to fishing. So this is even greater when talking about cold and deep water species. In Crozet and Kerguelen, there is the demersal longline fishery operating between 500 meters to 2,000 meters deep. And in Crozet in particular, they catch these skates on Taf between 500 meters to 1,800 meters. So we lack knowledge about most of its biology and ecological attributes, but we know that this skate is only distributed in Crozet and a little around. So my objectives are to determine vulnerability, which is a function between sensitivity and adaptability, and exposure to fishery. So I studied multiple parameters as growth, maturity, feeding ecology, but also interaction with the fishery to understand what's the impact of fishing on the skate population. So in Crozet, bycatch represent about 80 tons of captures a year. And since 2014, it is mandatory to release skates alive at sea, resulting in 90% of skates released. So the rule is to release skates after a condition assessment. So only skates that have mild injuries or no injuries have to be released. But since now, no one studied post-release survival of these skates. So you can wonder how much of this 90% of skates are really impacted by the fishery. So estimating post-release survival of the white-legged skate raised some challenges because we are in a data poor situation. We lack knowledge about biology and ecology of these species, and we have few possibilities of capture because it only relates on fishing vessels. So we set a capture protocol using a unique design adapted to our situation, and all of this within a limited time. So we knew that tag recapture rates in fish are really low and that we have only a limited number of fishing vessels. So we constrained the tagging effort in this small zone in the fishing area. We use dart tags that are internal tags, but are small and cheap, so we can tag thousands of individuals. And as for the management rule, we targeted good condition individuals only. As a consequence, in 2 years, we tagged 3,000 skates in this tagging area within the entire fishing area. So one scientist was on board the fishing vessel each year since 2020 to tag individuals. So all individuals captured in the fishing area was tagged. In 2 years, we recaptured more than 100 skates. So the first thing we learned is that skates survived to capture. And we recaptured them all within the tagging area, even if we have fishing all around the fishing area. So we also confirmed that skates have limited movements. Tag recapture rates were about 3.5%, which is similar with such study in fish. And we observed no difference between the tag recapture rate between individuals in good condition and indemned. So to sum up the situation, we have a capture event with the scientist on board. We tag and recapture, we release skates. And we have multiple recapture possibilities with a variable fishing effort. And then we have eventually a recapture on fishing vessel with uncontrolled conditions because no scientist is on board all fishing vessels. So we have uncontrolled conditions for the release of the skates. So we decided to don't release them, and we have a unique recapture data. To separate survival probability and detection probability, we kept them constant over time. So to describe the detection process, we use non-informative prior on the detection using the effort as covariate. Because effort, so fishing effort in number of hooks is really variable over time, ranging from 0, for example, to 800,000 hooks set in the fishing area, in the tagging area. For the survival process, after using multiple non-informative prior, we finally use this informative prior which match with the expected life history of skates. And yeah, for the results, we have posterior converge towards low value, and so we have a low detection value. There is the detection probability for the third period. But we were able to see the positive correlation between the fishing effort in number of hooks and the detection probability. For the survival, the model showed a high survival probability of 0.97. So this survival probability seems like the natural survival. So we are not able to disentangle natural and post-release survival. So as a conclusion and some perspective, because it's still a work in progress, we have a total amount of skates captured by the fishery, including 90% of them which are released at sea, with a high survival probability. But since we have a high correlation between survival and detection, we can wonder if we are really able to disentangle the two processes with our data poor situation, and if we can assess goodness of fit for this model. Within this 90% of skates released, a small proportion died after release. In this case, it is not significant, but we set the exact same protocol in Kerguelen. And for this species, Batyraja irasa, we obtain a recapture rate of 0.3%. For reminder, for Amblyraja taf, we had 3.5%. So in this particular case, it would be valuable to disentangle post-release survival and natural survival to obtain the impact of fishing. And to finish, we have 10% left skates that are not released. And since we seem to have post-release survival estimates higher than expected, we can ask if severely injured individuals can also survive, and if we can increase the total number of skates released at sea. So thank you for your attention.
All right, thanks, Joanna. That was a great talk. We have time for 2-3 questions. Okay, I'm not seeing any in the audience. I'm sort of just curious about how mortality would work with skates. Are they different from fish in that they don't have as much barotrauma? I know with fish, there's a much higher mortality than 98%.
Skates don't have swimming bladder as fish, so they have less barotraumatism as fish. And yeah, we expected a higher mortality rates, but maybe this species is very tough and have a tough skin. So maybe it explains also the difference with Kerguelen, where we have other species which are different.
Okay, thanks. And then I guess related to that too, it looked like maybe you were sampling over a depth gradient. And maybe with a survival of 98%, you wouldn't be able to tease out an effect. But would you imagine there would be an effect of depth as well on survival?
Yeah, we tried adding the depth as covariable, but it doesn't work. So, yeah.
Okay, great. Well, I think we're gonna end the session there. Let's thank Joanna and the rest of our speakers.
So before you all vanish for the break, we will have a look back to Euring 1992 in 10 minutes or so by Jean-Dominique Le Breton, who does not need any introduction, I guess. So it's my pleasure to have Jean-Dominique to give you this short talk about Euring 1992.
Well, good morning, everybody. I will present you indeed some memories of Euring 92, which we organized here, well, 31 years ago. Since I'm predating upon the coffee break, I will try to give some anecdotes, some pleasant anecdotes. I think one important message is that you will realize that all the classical stuff has been made by real people. And you have to think of people who in 30 years from now will look at the pictures of this conference and say, oh, this work was done by real people too. So, well, Apparently, we are 4 people here who attended the 92 conference. One is Steve Bailey. The other one is Todd Arnold. Where is Todd?
No, I didn't. I wasn't here in 92.
You were on the list, at least. I checked the list, or maybe, okay, sorry. And then Roger Pradel and me. So how does this work? I'm very bad with this type of thing. Well, it's a real pleasure, but the pleasure starts with the duty. The duty takes the form of an homage to Philip North. Philip North, who died 2 years ago, has been one of the key persons, if not the key person, to launch this series of Euring meetings. The story started by a joint meeting between the British Ecological Society and some kind of statistical society that led to this book co-edited with Byron Morgan. And Philip then was very active all along the Euring conferences, although he could not attend the 92 conference. In fact, he did not manage to get an academic position despite his very good scientific activity, and he turned to statistical consulting where he was very, very successful. So, well, he was a very important person and a very nice colleague. Now, here's the collective picture of Euring92. I can send you the original one. The conference was on invitation, and there were about 65 people plus a few locals. Some of you may possibly name some people from this peak, but I will show you more now. Some colleagues, Jean Claubert, whom many of you know, I guess, Nicolas Aebischer, who just retired from the, what's the name of the institution, Steve? The Game Conservancy. And Steve Piper from South Africa. Steve was, unfortunately, many people passed away among those I show. Steve was a very nice guy. He did splendid work on South African vultures. And he was a funny guy. I remember one day he started his talk saying, well, I have first to say I work in the psychology department in my university. And so everybody was kind of stunned, and he said, well, psychology, you know, the study of people who don't need to be studied by people who need to. Okay, Pertti Sorola, who was extremely active with the Euring organization at that time, and to the right, Lucas Jenny, Les Underhill, and John Tautin. That's fairly interesting because Lucas Jenny was responsible for the organization of the Swiss ringing system. Michael, he retired not 2 years ago. Yeah. Les Underhill was responsible for ringing in South Africa, and John Tautin was responsible for ringing in North America. You have to know that the organization of ringing based in Patuxent in the US works together with Canada and Mexico. So it's something like Euring. It's and Rob this morning remind you of the structure of Euring. A big thing of Euring is that from the very beginning, it included the Eastern countries, even before the Iron Wall disappeared. Okay, and the idea, and we use the invitations to introduce this balance, was to have a mix of biometricians and statisticians and population biologists. While statisticians are statisticians, they work on statistical questions. Maybe it's worth giving a short definition of biometrician. Biometricians start from the biological questions. They do statistics, but they start from the biological questions. So Byron Morgan is a very good example of a brilliant biometrician. And population biologist, André Dont came. It was at that time in Antwerp, working mostly on titmice populations. He moved since to Cornell. And Harry van Noordwijk, who is now emeritus in the Netherlands, was working at that time on various bird populations and especially on evolutionary aspect. He was a close colleague of Steve. He was at that time a close colleague of Steve Stearns. Okay, then, well, some other people. Anne Loison, who was at that time a student in Lyon, Mike Conroy, Nigel Yokos, who is now way north in Tromsø. And the one to the right is fairly funny because David Anderson and Ken Lacany at the 86th conference in Wageningen, well, David, those of you who knew him, David passed away 2 years ago. David was very good at having sharp and dry comments when something was wrong to him. And he gave such a comment to Lacany in 86, but well, 6 years later, they were able to stand close to each other. And well, one of the big events was George Joly accepted the invitation and came. George Joly was born, I think, in the early 20s. He passed away in 98. And here he is discussing with Neil Arneson. Neil Arneson is the person who developed the first multi-state capture-recapture models, together with Carl Schwartz. And to the right, you see George Joly receiving a gift book. And to the right, here's George Joly showing his book to Brian Manley. Brian Manley has been really the person who launched the strong tradition of biometry in Dunedin, on the South Island of New Zealand. And to the right, with Annette Hoffman, we are speaking with Richard Cormack. Richard was born in 35, he just turned 88. And well, are there people from St. Andrews here? Well, I guess that, well, at least not long ago, he was still going to the lab fairly regularly. He's still active. I exchange with him from time to time. So it was very nice to have these people together. In passing, there is a kind of a legend saying that Cormack and Joly did not go along very well because basically they wrote similar things 1 year apart and they were in the same building. And never communicated. But Richard wrote a splendid obituary for George Joly where he explained the city. He said, well, we were playing squash together, we are having a lot of activities, we never spoke of our research fields. And I really encourage you to have a look at Joly's 65 paper. It's, well, the algebra is terrible, it's very messy. In the obituary, but that was the way the subject was at that time. People were looking for explicit estimates and it was a complex model. In the obituary, Richard Cormack says that's a kind of algebra that is usually done between consenting adults in private. But now it's all handled by matrix formulas and hidden Markov chains and etc. But the comments in Joly's paper, if you really read between the lines, you will see that there's everything on several groups, multi-state and everything. It's really an illuminating paper. I really advise you to have a look. You skip the algebra, that's not a problem, but the text is really very good. Well, I think I can say among the Cormack, Joly, and Sieber paper, that's probably the strongest one in terms of vision. Okay, well, we had field trips in the Camargue, in the Montpellier backcountry. Here you see Jim Nichols with a Polish colleague where I was unable to remember his name. And to the right, you see Harry van Noordwijk with his nice hat. Wojciech Kania, colleague from Poland. Romain Julien, who is now in Paris in the same lab as Pierre-Yves here. Steve Buckland, who is in St. Andrews, far in the back. Steve just retired too, I think. Yeah. And Fred Cook to the foreground, right? Fred Cook is famous for his snow boots long-term program in La Perouse Bay on the Hudson Bay. I think it's the first long-term program that went over 100,000 birds marked. And as far as I know, the record, the world record is probably by Charles Brown on the Fleet Swallow with, I think, 350,000 birds marked. Okay, and we had the good social programs. Again, Steve Piper and Pertis Sorla, we were all given a bottle of local wine. Some people were not bad, were not good at that. They kept the bottle for 10 years, so they had excellent vinegar after 10 years. Okay, and one of the highlights of the social program was a visit to the Chateau de Flaugier, where the Earl Henri de Colbert, to the right, was welcoming us. You upper left, John Totin, Steve Piper, then two people whom I was unable to name, Gary White, the taller guy in the middle, and then Fred Cook and his wife, Sylvia. And Steve, I don't know if you remember, but we were, the two of us, up the staircase, and I vividly remember you told me, well, we are fairly good with eccentric nobles in Britain, but yours is really good. Okay. I wanted to show you a pic of Ken Dolan, but I have no pic of Ken from the conference, but I have the funny ones. Many of you possibly know that David Anderson was very keen on sports cars. He had one of the 12 Lamborghini contacts in the US. And at the Pescara conference in 27, I think, we discovered a Lamborghini tractor. So we told Ken, go up to me the pic. So that's Ken with his Lamborghini. Obviously, we sent the pic to David, who was not in Pescara. Okay, and I cannot conclude without showing you a pic of George Sieber. George Sieber was born in 1938 on the 6th of April, so he just turned 85. He's good health, very productive, writing books, being active in humanitarian organizations. He's a very nice man, and we are very fortunate to have this Euring conference in Dunedin in 2004, I think, or 07, I don't remember, where he attended. He hates traveling by air, so traveling to the South Island in New Zealand was okay from Auckland, but not far away, and all those who were at this conference were happy interacting with him. Okay, that's it.
Coffee break, 15 minutes.
Oh, thinning. Yeah. Thinning. Okay, yeah. I know that you were starting to see that. Imagine how like a present tense, like how having repeating an app, like how having yesterday. Okay. I always see that.
I know for me, I go back
Yes. Hi, Michael.
Hi, nice to meet you.
Nice to meet you. So you are the first speaker, and your name is Jewel, or do you say, or how do we pronounce?
That was on some of the best. Yes, it's Jewel.
Jewel, okay.
Yeah. Usually people say Jewel, so yeah, you were very close.
Okay.
That's the closest I've ever heard it.
Okay.
Yeah.
Are you working with Phil Temple? Okay. And then you are in Fort Collins then, or not?
I got my PhD from Colorado State, but I'm working in Flagstaff.
Okay. Okay. Yeah, I see.
With Charles Appeal, yeah.
I don't know why.
If you want to see, oh, it's here. This one. No, maybe. Yep, I see. And I have to. Oh, okay.
Est-ce qu'on switch on le micro?
Ah, c'est off.
So welcome back, everybody. Now we have the session on survival and movement in context, and our first speaker is Maria Jewel. She will talk about, can true survival be estimated without global insight, resight, sorry. It depends on true movement.
All right, can everyone hear me okay?
Okay. Well, thanks for this. I've had such a great time at this conference. So I just wanted to thank the organizers and everybody here. It's been a great experience. But yeah, I'd like to acknowledge my co-authors, Charles Kulik and Bill Kendall. So today I'm going to be talking a lot about the Barker model, which uses discrete capture occasions and continuous recite intervals. So you have discrete capture occasions where sampling occurs within a sample site, and outside that sample site, individuals are not observable. And then you pair each discrete capture occasion with a prolonged recite interval where animals are observable both inside and outside the study area. And these prolonged intervals violate a lot of the assumptions of most mark recapture models, which assume that sampling occurs in discrete time kind of instantaneously. And if you were to bin all your recites into a single capture occasion and treat it as though it occurred in discrete time, you would get biases in survival. And so this model is kind of designed with those continuous data in mind. And you might, if for example, you might use it if you have citizen science and people are reporting bird bands throughout the course of a season or the year, like some really long interval. And also, a lot of new technologies like RFID detectors, camera traps, MODIS towers, those are all technologies that could detect tags continuously. So might be useful to put in a Barker model. The parameters of the Barker include survival, and then F and F prime both describe movement in and out of the sample area, capture probability, recite probability, and then there's R prime, which is the probability an animal is recited before it dies. And you can also include dead recoveries, which is little r, but in this, I'm not including any dead recoveries, so I just fixed that to 0. So we're interested with survival with the Barker model. Everything else can be considered a nuisance parameter. And this R prime is kind of a big nuisance parameter. It's not very biologically meaningful, but by including it in the model, that is kind of the key piece that allows you to get unbiased survival estimates with continuous recite data. So I wanted to use some simulations, and I work in rivers. So these little squiggly lines are supposed to be rivers. And I have a sample site, that's the green, and 5 different occasions. And if I had data like that in the sample site, I could fit a CJS model. But the problem with that is that it only estimates apparent survival. So, if fish die or if they move outside of the sample area, those two things are confounded. So I might try to think about ways to improve upon the model or get a better estimate of true survival using recites. And there's a few ways to do that. So I'm just going to test out some sampling designs using simulation. So there's a global recite, which is kind of the ideal, but maybe not always achievable, where you can recite throughout the study area. And then you might have like a random recite where you just visit sites randomly, and that differs, according to the time occasion. You can also have fixed sites for recite, and there's 2 different flavors of this. Up here, the sample site is excluded from the fixed recite sites, and down here, it's included in the fixed recite sites. And then you can have combinations of both fixed and random for recite that both include and exclude the sample site. And I just wanted to focus on that. A lot of the comparison will be about these fixed sites and whether or not you include the sample site as part of the recite or not. So I use simulation to look at this. I fixed F prime to be 0, which just means I'm simulating and fitting a model with permanent emigration from the study site. I tried to have pretty high recite and recapture probabilities and Markovian movement. And I have, in addition to the reference, I have a low capture probability scenario, a high survival scenario, and a high movement scenario. So here are some results. So both the global and the random recite had 0, were pretty much unbiased, more or less. When you included the sample site as part of the recite, you got negative survival bias. And this kind of makes sense because it's kind of like a CJS in some ways that, if an animal leaves the sample site and it lands in one of the blue areas, which is non-recitable, that's confounded with mortality. So you would kind of expect a negative survival bias in that case. But if you have, in the yellow and the green, which have high survival, high movement, you have less bias just because you have more opportunity to see those individuals on future occasions. Now, if you exclude the sample site from the recite, you can actually get positive survival bias. And in some ways, this, what you're kind of creating is you're creating like one group of individuals has highly recapturable. Those are the ones in the study site. And you have a separate group that's highly recitable that's in those recite sites. And those are two separate groups. And so it violates a lot of the assumptions of the model and just creates positive bias in survival. If I had fit a CJS to these data, I would have had a much stronger negative survival bias. That would have been much, negative 0.5, so way down here somewhere. So I did some goodness of fit diagnostics using the CHAT simulation tool in Program Mark, which is not perfect, but still a really useful tool. And the CHATs for a lot of these were really close to 1. So you wouldn't necessarily diagnose these kinds of issues with goodness of fit with the CHAT simulation tool in Mark anyway. So in conclusion, the sampling design for recite data matters. If you have a global or a random recite, that's great. But if you're thinking about using fixed recite sites, that might be, have to think about whether that's appropriate. A lot of these like new technologies, like I know in the fish world, a lot of people are using pit antenna arrays, which are, they do detect tags continuously, so they fit the Barker model in that sense, but they're fixed in their locations. And so just trying to figure out how to incorporate that into your sampling design and your model so you can avoid survival biases if possible. So if you include the sample site in the recite, you'll get negative survival bias. So it's still parent survival, but you'll do better than a CJS. However, if you exclude the sample site from the recite, you will get a positive survival bias. So that should probably be avoided. If you have more mobile, random movements of animals, you will have lower, that will help lower your bias. So just knowing more about your organism is helpful. And this bias exists. I presented on F prime being fixed to 0, so assuming permanent emigration, but even if you fit a model where you don't do that, where you have immigration and emigration from the sample site, you can still get bias. The results are very similar. And you can't always diagnose these issues with CHAT. So that's all I have. Thanks.
Thank you very much, Maria. Questions?
Thanks for a very interesting talk. I was wondering with the random recite areas, did you just I guess if they're random, you somehow simulated where they were going to be. Did you do that several times? And are there any indications that the way they are spread out affects the parameter estimation at all?
I mean, the way I simulated the data, the Barker model just has it's a single state model, but it's just, whether or not you're in the sample site or anywhere else. So if you're outside the sample site, it doesn't really matter where you are outside the sample site, as long as, as long as that area has some recite probability. I don't know if that answered your question or not. Okay.
I'm thinking of applying this to birds, and I know you're thinking fish, so you're not obligated to answer, but And maybe the majority of re-encounters outside of a banding period might be near a ringing or banding station. And it seems from your simulation results, you're damned if you do and you're damned if you don't, if you include or you drop those.
Yeah, I mean, one thing that I was trying to do, but kind of ran out of time is, and I can't give you like definitive answers on this, but there's a multi-state Barker version in Program Mark where, you can have, so you could actually have different recite probabilities for inside and outside the sample site. I mean, you're losing information with this model too. Like if you capture it outside the sample site, it's simple. It's really appealing because it's simple, but you're not using that information where you capture it. So I think there's something certainly to be gained. My limited experience with where I've gotten so far, I think there's something to be gained by going to the multi-state Barker, but I'm not fully there yet, so I didn't want to present on that.
So we have a question also from the internet, from Jamie Sanderlin. She said, thank you for the great talk. What are the relative costs between the sampling designs?
Yeah, well, it's a good point. Yes. So like the global, I put the global recite up there, but like for my study system, that's not achievable. The random recite in my system is not achievable either because we have really low capture probabilities. So if you were just to like visit randomly sites that had like no previously tagged fish or very few previously tagged fish, you just wouldn't get enough recaptures to even fit a model. And so, I mean, I think, yeah, in terms of the study design, I think it would depend on the project, what's feasible in terms of what, whether fixed or random sites are more economically feasible. But yeah, this is just a simulation tool. So I guess it just depends on what you're studying.
Okay, then we move on to the next speaker. So our next speaker is Saskia Schirmer, and her talk is about seasonal and spatial explicit survival estimates, combining the multinomial re-encounter model with an individual-based temporal model.
So hello, everyone. My work is still in progress, as you will see, but I brought you an example data set for the introduction. So I have ospreys, which were marked in Europe, and you can see here the point pattern of the dead re-encounters in red, and they can be used to estimate survival. When we split up the data set to the different seasons, you can see that the point pattern differs. You can easily imagine that an individual which will be found dead in fall just survived from summer to fall, but an individual which will be found dead in spring will survive from summer to fall, and then from fall to winter, and from winter to spring. So a much longer time span. But when we estimate only annual survival, all these points will have the same impact on the survival estimate. So the question is, why do we not just model seasonally, temporally, and spatially varying survival while accounting for everything else, meaning migratory connectivity and the re-encounter probability? The short answer to this is there is no model which fits all. The longer answer is there are at least two models which fit part of it. So there is the multinomial re-encounter model, which works on the population level. And it basically says that when you know the number of marked individuals in an area of origin and the number of dead re-encounters in an area of destination, then you can estimate the proportion in which the populations of origin go to these destination areas, and the survival and recovery probability for the different destination areas. This is nice, but all these parameters are constant over time, which also means that they are constant over seasons and over age classes. So we have another model, an individual-based temporal model, which means that we have one individual which can survive from year by the different survival probabilities. And when it dies, it will die by the inverse probability and might be found by a recovery probability. Here we have temporal parameters, but we don't use any spatial information. So the ideal case would be that we can use the temporal model to have a seasonal model, and then in every season we have a multinomial re-encounter model to estimate the spatial parameters. Then we would have seasonal and spatial survival, migratory connectivity, and recovery probability. The main problem is that to do that, we need to know the number of individuals which are available for surviving or for dying and being recovered. So the number of available individuals is represented by these blue boxes up there. And we know it for the first time step because this is just the number of marked individuals. But and we can also see that these boxes get smaller and the size decreases by the temporal survival probability. So why is this the main problem? This is because when we have the case that we have two areas of origin, so we have 2 times the available number of individuals, and we have 2 destination areas seen here in blue and green, and we would know how big the size of these boxes up there are, then we can just estimate by the multinomial re-encounter model the proportion for, so the blue and the green proportion here, and then we can just estimate the survival parameters and the re-encounter probability and the migratory connectivity. So we use the temporal model. So when we use the temporal model, we know the number of markings in the first time step. And when we can identify survival probability, then we also can model the size of the second box here. When we look at when the temporal survival probability is identifiable, we can find this, for example, in the paper of Cole, 2012. We know that we need 1 cohort for every time step. So only when we have a second cohort at the second time step and we see the dead re-encounters of the second time step, then we can identify the survival of the first time step and we can identify the recovery probability of the first time step. And only when we get a third cohort on the third time step and see the recovery probability of the third time step, we can identify the survival of the second time step and the recovery probability of the second time step. So this is quite nice because it means when we have these data, then we can also have a temporal version of the multinomial re-encounter model. The problem is I wanted to have a model for seasonal survival, and normally when we have seasonal data, we don't have this information. So for example, for the osprey data set, the marking events take only place in the breeding area, so this is only 1 time per year, and we don't have any information on the 3 other seasons. So we can still estimate annual survival, but no seasonal survival. This is sad because I don't have any estimates for the osprey. I still don't have any estimates. And it's also sad because there are so many problems to solve when you have this situation and you, under the assumption that you can identify survival. And I would rather have told you that than that it is not working. But there is still some hope. Well, maybe no hope. I know that I might be able to tell you in a later conference, because when we have a live capture recaptures, the probability, no, the next cohort does not only consist of the newly marked individuals, but also of the recaptured and released. So if we might have a data set where we have enough recaptured and released, we don't need these newly marked individuals and we can still estimate seasonal survival. This might be not true for the Osprey data set, but maybe for other data sets. And the other option is then that we can combine it with other data types. So for example, coloring data or tracking data. So the take-home message is, if in any case where temporal survival is identifiable, we also can have a temporal version of the multinomial re-encounter model. And for seasonal data, which means that we don't have any marking events in all seasons, survival may still be modeled in combination with other data types. That's it. I want to thank all the people who provided the Osprey data to me and you for listening.
Thanks a lot, Saskia. Are there any questions, Saskia? Oh.
Thank you. That was really interesting. Cool model. Sad it doesn't work. Can you say a little bit more about the metric of migratory connectivity that you were talking about? What is that actually telling you?
So what is the question?
What does the metric of migratory connectivity that the model is going to return? What is that actually telling you?
So so you have a breeding population or some population of origin, and the migratory connectivity is just the proportion from. So there's an assumption that every individual from this origin population will go somewhere. For example, to a wintering area or to a migration, so they will migrate somewhere, even if they die before, but they will go somewhere. And then you have just the proportions to go to the different wintering areas or the proportions to go to the different destination areas.
Okay, so for one region in the breeding season, you would have a measure of the proportion of individuals that go to another region in the non-breeding area.
Yes.
From that. Yeah, cool.
If you could use your model to estimate the amount of ringing effort necessary during alternate seasons in order to be able to get reliable estimates for your osprey population.
So I don't know if this is what you want to, but well, yeah, I thought it would work because I can just model the size of the next box. But the problem is that I can only model the next box if I know the survival first. And I only know the survival when I have a ringing event in the next season. So this, it's like going forth and back. This is not working.
Okay, then would like to thank Saskia again. Then we turn to our next speaker, which is Jaume Badia-Boher. He's talking about evaluating permanent emigration and subsequent biases in survival in territorial raptors using spatial capture recapture methods. The case of the Bonelli seal.
Morning, everybody. Thank you very much. We're going to talk again about the amazing Bonelli seal, and let's see if this works. Okay. Yeah, I guess this is, everybody knows about that already. But basically, when we estimate survival in MAR recapture schemes, we can basically estimate either apparent or true survival. We normally cannot choose which one to estimate. It's to some extent like an obligation depending on the study, on the type of data we have, and also the study design that we have. Basically, the difference is between apparent survival and true survival. I guess you know, apparent survival is the product of survival and site fidelity. It's probably the most reported type of survival because many MAR recapture schemes cannot differentiate between permanent immigration and mortality. Essentially, when an individual leaves permanently a study area, it cannot be resited anymore. And this is why the models confound between mortality and permanent immigration. And this is why apparent survival is so widely used. Then we have true survival, which is actually a neat estimate of survival. It doesn't have the effect of permanent emigration, but of course, in many cases, it might be difficult to estimate. So, which of both estimates is better? As many other questions in the field of ecology, the answer is it depends. But I will show you a case in which I believe that true survival is better. So, for example, when we want to study populations that can be staged into different, that can be structured into different population stages. Like, for example, you might expect that there are differences in survival between age or between sex, and you want to study this difference, I don't know, for example, for conservation purposes, perhaps true survival is better. And I will tell you why, using the Bonelli's eagle as an example. I believe that this example is widely applicable to other species. Basically, permanent emigration depends on mostly or mainly in many species on natal dispersal. Natal dispersal, you know, the movement between an area of birth and the area of first breeding. Usually in many species, natal dispersal comprises like the longest movements in an individual's lifetime, then the movements that can most likely end up in permanent emigration. In the case of the Bonelli's eagle, this is even more this is even harder because the Bonelli's eagle, whenever it does natal dispersal, it usually doesn't move much anymore. So when it starts breeding, it doesn't abandon the territory of first breeding. So basically, in the Bonelli's eagle, natal dispersal is the driver of permanent emigration in this case. The problem of natal dispersal is that, for example, if you check here, natal dispersal usually shows differences among population stages. Like, for example, in many birds, as in the case of the Bonelli's eagle, you will see that females tend to disperse longer than males. This is the case also of many birds, but for example, in mammals, it's usually the opposite. Males usually tend to disperse longer than females. So probably there's one sex that's more affected by permanent emigration than the other sex. But then you have a problem with age as well, because, for example, in many long-life species, in many long-life birds as well, the age of first breeding is not a deterministic value. It actually varies with age. You have to estimate it. Here you have, for example, the probabilities for the Bonelli's eagle. It first increases, then it decreases. But this is just, let's say, a photo of a specific moment of the life history of the species. For example, age of first breeding can vary a lot. For example, along with density-dependent processes when the population is increasing, when the population is decreasing. So in the end, what I want to say is that the intensity of permanent emigration processes can vary between population stages. If we estimate apparent survival and try to assess differences between population stages in survival using apparent survival, we will never know if the differences are because of permanent emigration or because of survival. So I hope I have convinced you that in this case, true survival is better. There's a few ways to estimate true survival. For example, there's the robust design, the Barker models. Here we're going to talk about spatially explicit mark recapture models, which are, I guess, growing in popularity now with the Bayesian framework. We could be talking about this for 2 hours. Unfortunately, I only have 10 minutes, so I will be very, very brief in this case. Basically, these spatially explicit mark recapture models have mostly two subcomponents. There is the mark recapture subcomponent, in which you have your life history, your mark encounter data. And then you also have your spatial submodel with your dispersal data. In our case, our natal dispersal data. And we basically model natal dispersal in the individuals included in the mark recapture submodel. So we model natal dispersal as a random draw from a statistical distribution. And if the individual happens to leave the study area permanently, this is of course considered a case of permanent emigration. This way, basically, we are informing the model that there's many ways to not be recycled anymore in the study area. It might be because of mortality, it might be because of other reasons, and it might be also because of permanent emigration. And this way we can estimate true survival, and we can also estimate permanent emigration. So let's move to species. This is our study area, Catalonia. As you can see, it's a part of the metapopulation of the species in the Western Europe. We know that the species disperses to other populations. The lucky part in our study is that many other populations, not all but many, also have monitoring programs, so we can know about individuals leaving and moving to other populations. Like, for example, here in France, where we got a very nice presentation yesterday. So what we can do here is to estimate apparent and true survival. We can estimate apparent survival if we only account for resightings from our local study area, and we can estimate true survival and permanent emigration if we extend our ability to see our resightings to most of the monitored populations in the metapopulation. And we use this spatial model I told you about before. So basically the aim of our study was to estimate true survival and apparent survival by age and by sex, and also permanent immigration probabilities in our study area. All right, time for results. I would say basically this is females and males, different age classes, and survival probabilities. Apparent is teal, true survival is blue. There's probably three main messages in this graph. The first one is that yes, indeed, there is differences between apparent survival and true survival. The second message is that these differences are more intense in females, as expected, because females have probably larger probabilities of permanent immigration. The other message is that yes, the differences between true and apparent survival vary by age. And actually, for example, here in 2- and 3-year-olds, the differences are larger in females, but in females, more or less, the larger differences are in juveniles. So there is also differences probably in the age of first breeding of males and females that cause these other differences. In the end, what I want to say is that when you estimate apparent survival in a population structured by stages, the biases or the differences, the effect of permanent immigration will not be very predictable if you don't have information about the age of first breeding. So you might say these differences, and you may see these differences and think, so is this, what's the impact of that? For example, we could get these sets of estimates of apparent survival and true survival and project the population using a population viability analysis. We could do that. You can see that the differences are enough to predict completely two different population trajectories. When we use true survival, the population is more or less stable, even increasing. When we use apparent survival, the population tends to decrease quite a lot. Of course, I think that in this case, true survival is predicting way better what's happening now in the population because it's increasing, but I'm not saying that true survival is better in all population viability analysis. Indeed, there might be other cases in which apparent survival is actually more adequate. Okay, let's move to permanent immigration probabilities. This is the permanent immigration probability, basically the probability of an individual to leave our study area after natal dispersal. It is about 38%, but of course this probability is not homogeneous in space. So for example, if we map this probability across space, the first thing that we will see is that in females it is larger than in males. This was also expectable. But also an interesting message of this map is that there exists the border effect, which means that if you are if you are born close to the border of your study population, the most likely thing will be that you will end up outside of it, especially in females instead of males. If you are born in the center of the study population, the most likely thing is that you stay in the study population. All right, we are publishing this in scientific reports. We are already with the proofs and with the payments. Hopefully, in a couple of weeks, you will be able to check it. This was just a brief summary. There's many other things in the paper. We are also testing the effectiveness of the estimation when the data, recycling data, is very limited in space. We are also doing many other things. Yeah, I think it's cool. Have a check on it. I liked it a lot. That's everything. If you have any questions, I will be happy to answer. Thank you.
Thanks a lot, Jaume. Are there questions in the audience?
Great talk. Thank you. First, I'm dying to see one of these Bonelli's eagles.
Let's hope so.
I've seen so many talks, they seem like cool birds. My question is about, it seems like, are these birds limited by territory availability? And how would that density dependence factor play in your model or affect your results?
Yeah, that's a very interesting question. And I believe that our estimates of the age of first breeding are already a result of density-dependent processes. But yeah, it's actually limited by territory availability. I would say that this is a very difficult thing to model. We don't have much information about that because to some extent the population is limited by territory availability. And you see these density-dependent processes. To the other extent, sometimes you see eagles like creating new territories that were not occupied before. So we didn't have enough information to model that. I believe that there might be an effect, however.
There's another question.
Do you see it sort of a trade-off with cost benefit when trying to decide if you want to use apparent survival versus true survival? Because it's probably costs more to collect data to get the true survival, right? Or is it just a different model?
Could you please repeat it, the first part of the question?
Yeah, I was wondering if you see it as like a cost-benefit ratio, does it cost more to estimate true survival compared to apparent survival?
Yes, for sure. I would say that we are lucky in our study system because there's lots of populations that are monitored. Of course, there is some costs. True survival is sometimes you need more monitoring, and this often translates in more money, actually. I think that more or less what the results show is that if you don't have enough data to estimate true survival, and especially in long-life species, if you want to evaluate these differences in survival within different population stages, and then you want to draw conclusions for conservations, you at least should be careful.
Okay, let's thank again, Jaume. And then we will have our last talk of this session by Murray Christian, and he's talking about accurately estimating the demographic contribution of immigration, a southern elephant seal case study.
Okay, sorry, just acquainting myself with the technology. Okay, so yeah, thanks very much. And the work I'm going to talk about today is part of my postdoc, and it's sort of manuscript in preparation. It'll be shipped soon, and it's joined with Chris Oosthuizen and Nico de Bruin. So I resisted the temptation to call my title "How Mathieu Paquet Made My Postdoc Harder but More Interesting." It'll be very closely related to the first half of his talk. Okay, so we're in the game of understanding the drivers of population dynamics, and here's a sort of schematic. We get some data suggesting a trend on the top left. We'd like to know what's responsible for that at the demographic level. So there's a very nice analytical framework, a formal framework for getting nice answers for this, where we couple integrated population models to a transient life table response experiment. And we get an answer that looks like this, where we get contributions from different demographic factors to the temporal variance in population growth rate. And we can see, for instance, here, immigration looks really important, juvenile survival is more important than adult survival, and so on. I'll talk a bit more about, yeah, okay. All right, so we're working on elephant seals. At least one of them is quite happy for the attention. It's a long-term mark recapture study, about 40 years, 9,500 tagged female seals. It's a female-based model, and yeah. Okay, so at the heart of every IPM is a latent population model on which you can condition different types of data. And our latent population model is sort of captured by this life cycle diagram. So these things take a few years to mature. These PBs are pre-breeders of a couple of ages. They can start breeding age 3, then they move into this breeding class. The breeders can sometimes skip years into this non-breeding class, and we account for that with a multi-event model. And immigration is also important for this. There's a priori information that immigration is important here, and probably those come from the French islands, the Kerguelen Islands, if I'm saying that even remotely correctly. Okay, so we have immigrants, and these are new immigrants, and after they've arrived and bred for the first time on Marion, we incorporate them into a breeder or non-breeder class. Okay, yeah, data pretty standard, mark recapture, population counts. Usually there'll be some fecundity data here, but elephant seals just have one pup when they breed, so there's nothing to model there. And our estimans is all the stuff in this image, and then as a result, we get the population growth rate as a derived parameter. Okay, so for those not initiated into the dark art of estimating immigration from an IPM, I'd like to just maybe give you a little intuition. some heuristics about how I think information flows in the model. So for me, what's doing the heavy lifting is the mark, or in our case, what's doing the heavy lifting is the mark recapture data. That allows you to estimate vital rates, taking into account some nuisance parameters. And then once you know the vital rates, who's surviving and when, then you can kind of project the population forward. And that gives you sort of a known with uncertainty, but let's say known value for breeders in all the years. And then basically breeders plus immigrants equals the count. And so you know the count, you know the breeders, and immigrants is the difference, heuristically speaking. Okay, but this means that immigration is not directly informed by any data, and therefore it has all sorts of issues with its estimation, as Mathieu described to us in detail yesterday. One of these is that the bias, if there is bias in other parts of your model, that can easily propagate to immigration. And another is that immigration can kind of absorb unobserved variation in your model. And that can be a real problem for these downstream analyses, these transient life table response experiments, where you're interested in temporal variation. So estimating immigration is dangerous, but we went ahead and did it anyway. We fitted our IPM in STAN, we calculated our life table response experiments, and we got this. And it looks like immigration is the most important thing for this population, or it could be. Damn it. So now we have to see if this is robust. You know, how much confidence can we really have in this conclusion? And we did two things to try and understand that. The first is we followed the recommendations in their paper, and we simulated data under our model with 3 different levels of temporal variation in immigration, low, medium, or high. Then we compute the true demographic contribution and the estimated demographic contribution and see how the model does. So when the true contribution is quite low, it's biased high, the coverage is apocalyptic, and we were expecting that, okay. For the medium contribution, the coverage is quite good actually, but it's starting to show a little bit more of this trend that you see here when the truth is high, is that our model is actually underestimating the demographic contribution for when the truth is large. And I'm at a bit of a loss to explain that. But in terms of where our contribution fits in here, our posterior median's up here. So it looks like we're sort of outside the range where this could be explained by no temporal variation and just estimate of pure noise. So cautiously optimistic that we're getting a robust biological conclusion, if not a statistical estimate. Okay, and the second thing we did is we looked at sensitivity to regularizing priors. So immigration is a weakly informed variable, and when that happens, you can expect your priors to have quite a lot to say about your posterior estimates. And so what's a regularizing prior? Well, sometimes model estimates need to be constrained a bit. In the maximum likelihood framework, this might mean a penalized likelihood. In Bayesian setting, we can use prior structures to achieve this. And Mathieu's paper really showed that if you don't put any regularizing prior on immigration, your estimates are worthless. They're totally off. So some regularizing prior is required, but then it's a question of what one do you choose and how much do your results depend on that choice. So we looked at 2 kinds of priors, these kinds of shrinkage priors, which is like a temporal random effect. And then we played around with a bit more interesting creature, Gaussian process priors. So the gesture for shrinkage priors is this, and the gesture for Gaussian process priors is this. Okay, and this image really makes 2 comparisons. There's the comparisons between the light blue and the dark blue, and that's, well, let me first say, as you can see, your prior choices can have quite a big impact on your ultimate estimate in immigration. And comparing the light blue to the dark blue is a comparison between the priors, not on immigration, but on the vital rates. So this is back in the IPM. So what we're doing to our priors in the IPM is having an effect on what's happening to our TLTRE estimates. That's an interesting story. If we have time, maybe you can ask about it later, but I'm gonna focus now on, well, so it's an interesting story where this difference comes from, what that's about. But I'm gonna focus on this other comparison, which is between having a temporal random effect prior on immigration and a Gaussian process prior on immigration. And so here are the annual estimates under those two models. And you can see that compared to the temporal random effect, this Gaussian process is doing a couple of things. So one is it's kind of smoothing the annual estimates. And that's because of the way it shares information between, it induces correlations between estimates in nearby years, and it has the smoothing effect. And you can also, so for instance, this kind of apparent outlier here is kind of smoothed more into the general pattern. And you can see these posterior marginal variances are shrunk quite a lot as well. And that's nice, because if we think that this is absorbing residual variation, if this model can kind of push some of that residual variation back out into the other variables where it makes less of an effect because they're informed by data, then this might be quite a nice device. And then one other thing is that these this prior seems to also be, this Gaussian process prior seems to also be flexible enough to capture trends, things that you want real signal in the temporal variance in immigration. So I think these might be interesting going forward. Yeah, so conclusions, cautiously optimistic that immigration is important for our elephant seals on Marion Island. But it's a real challenge when you're doing this to know if you can trust the estimate. So just to echo the recommendations of the two, simulate. And I would encourage people to look at the sensitivity of the results to these multivariate priors that you place on immigration and even the vital rates, and not to take the estimate at face value. And something I'm interested in looking at a bit more, and I'd love to discuss with any of you if you're interested, is there anything we can do with regularization to improve the way these models estimate immigration? Okay, I think that's all from me. So a big thanks to the conference for being here. It's been great, and for the support in getting out here. And please, if you'd like to discuss this, I'd love to meet more of you before I head back to South Africa. So thanks.
Thanks a lot. We have time for one question.
Question. Do you know the origin of the immigrants? And would they come from the large population of Kerguelen or South Georgia, or the tiny one from Crozet that is heavily impacted by predation by orcas?
My colleagues tell me they probably come from Kerguelen, but there's very limited direct evidence of that. Yeah.
Okay, last question. Another one? No? Ah, there was none.
Okay.
So, thanks for a great talk. Biologically, how sensible do you think it is to do year-to-year smoothing on these immigrations? Like, do you think that makes sense, or do you think the immigration happens in pulses and is actually very stochastic from year to year?
Yeah, that's a great question. Thanks. I think it's going to depend on whether you want. I think there's going to be a trade-off between your accuracy in the estimates in the individual years and your accuracy for the downstream analysis with these live table response experiments. And this is looking more at that accuracy in the downstream analysis. Yeah, that regularization may well induce some bias, and yeah, maybe inappropriate if you have big pulses, as you say.
Okay, then thank you very much, Christian, and also all the
Okay, three things. Difficult to say. Okay, first one, it's time for group picture. So it will happen down the campus where we have lunch. Okay, now. Second thing, excursions. For those of you who weren't on time at 9. So we will meet at the entrance or the exit at 1:15. So Well, you can be sure that we will ring the bell